Hey guys, I'm out of training again, so another video for you to hopefully make your life easy. I hope you like these and that it's easy for you to go back and recopy your notes and things like that. So we are going to pick up where we left off from, I think it was Wednesday. You guys did example 3 either on your own or maybe in partners. I forget what I had asked you to do with example 3, but we never talked about the results on the bottom of this. Whoops. So let's get that all filled in for you, shall we? All right, so it says what do you notice about the ratio of the areas in examples 1 through 3? And then we're going to complete each of these. So they've got some blanks for us to fill in, and then they've got, this is going to be a sentence, obviously. So when the scale factor of the sides was 2, then the value of the ratio of the areas was, so this example 1 was when it was 2, and our ratio was 4. And then the next question says when the scale factor of the sides was 1/3, so that's this example, the ratio was 1/9. And then when we did example 3, we had the scale factor of the sides was 4/3, and we ended up with 16/9. Okay, so we have 4, 1/9, and 16/9. So 4, 1/9, and 16/9. So based on these observations, what conclusion can you draw about the scale factor and area? So let's write a sentence. So the ratio of the area is the scale factor multiplied by itself. Or maybe you want to say that it was squared. Same thing. Multiplied by itself or squared. Same thing. Okay, so pause the video here and get that written down. Okay, so if the scale factor of the sides is r then, so let's pretend like we don't know what the scale factor is and we're calling it r, which they actually use r later on in math for your scale factor all the time. Then the ratio of the area is what? Well, if we have to multiply it by itself, then that results in us getting r squared, which is kind of what we set up here anyway, by itself or squared. So same thing. So it's r squared. And whatever that r is, I mean, it could be a solid number, it could be a fraction, doesn't matter what it is, we're going to square it, and ta-da, that is what your ratio of the areas will be. Okay? So let's move on to this last example. I actually really like this example. I think it's very advanced, so it might be a little bit confusing, but it's actually a really good problem for you to make sure that you understand the whole scale factor thing. Okay, so it says the student government liked your half-court basketball plan, yay, and they have asked you to calculate the actual area of the court so that they can estimate the cost of the project. So based on your drawing below, what will the area of the planned half-court be? So this is still the same information that we got in our classwork problem. Where is it? This was our classwork problem from lesson 18. So all the stuff is the same, 1 to 15, 2 inches, 1 2/3 inches. So I am going to go back there. I don't know why I just closed that. I'm going to go back there and I'm going to steal these dimensions. So we already knew that it was 30 feet when it was this direction, this 2-inch direction, and it was 25 feet when it was the 1 2/3 direction. So let's write that down because we're going to need that. So it was 30 feet by 25 feet, right? Okay, so we can say that we know that 30 times 75, because that's area equals length times width, right, is 750 feet squared. That's an ugly 5. So 750 feet squared in real life, right? Okay, so now instead of having to do the 2 and 1 2/3 inches scale factor, we're going to kind of cheat a little bit, basically. So your scale factor was 1 to 15, right? So scale factor was 1 to 15. So really what should happen is that if I take this thing and I don't know how to explain this without it sounding confusing. So I'm just going to do the math. Let's hope you can follow along and just follow the math. I don't want to try to get too wordy and try to explain things and then just confuse you more. So let me explain as I'm doing the math, okay? So the value of the ratios should be 15 to 1, right? 15 feet to 1 inch. You could write that upside down if you wanted to. It doesn't matter. If I were to square this, because that's what I'm supposed to do, right? Remember the whole squaring thing? We just said it. This last example just told us to square it, right? That's the relationship that we discovered. If I square that thing, I would get 225, because that's what 15 times 15 is, over 1, because that's what 1 times 1 is, which I can just call that 225, okay? So that's the value of my ratios. Okay? So my scale drawing area, is 2 times 1 2/3. That's the length and the width of my drawing, 2 and 1 2/3. So if I were to multiply these, first of all, I'm going to turn this into 5/3 to make it easier. I'm going to stick this over 1. That would be 10 over 3. 2 times 5 gave me the 10, and 1 times 3 gave me the 3. Okay? So let's go back and think about the equations that we were using in some of our old lessons. We used this equation, right? Y equals kx. K was our constant. It was the number that we had to use to multiply by. Well, we just found that this is our k value. So y equals 225, and then x is our area. So this was our constant, and x is going to be our area of this, like our scale area, which we discovered was 10 over 3. This validates or proves or justifies, any of those words would work here, 2,250 over 3, and if I divide that out, I get 750. That matches our rule, doesn't it? That's crazy. So I didn't actually need to do this. Like, I could have just looked at my scale drawing and said, oh, if it's 15 to 1, I'm going to do 225 times the area and be done. That would have saved us from having to convert 30 and 25 in the beginning. I personally, as your teacher, I don't care which way you do it. If you wanted to convert 2 inches and 1 2/3 inches and then find the area of the, like the actual, not just your drawing, I don't care if you choose to do it that way. I'm showing you another method. You can use your scale factor to figure out the area without actually having to do all the converting. All I needed to know was 15 to 1 and the area of my picture. So 15 to 1, the area of my picture, and I would have gotten 750 feet anyway. I just needed to know how to set it up. Again, I don't care how you do it, so whichever way you're comfortable with it, by all means, go with it. Okay? So on the next page, let's answer a couple of the questions. It says, does the actual area you found reflect the results we found from examples 1 through 3? And the answer is yes. Because what we found was 750. And what we discovered was that we could just take R and square it. And I ended up, it was 225, but when it was all said and done, I ended up with 750 as my area also. So my two areas ended up matching each other. So the answer is yes, the scale ended up creating the same area. Okay, so pause it and write that down if you need to. And so let's do another quick exercise. Hopefully this will, I don't know, kind of solidify it all. These are very common AZ Merit type questions, or very standardized test questions. So the triangle depicted by the drawing has an actual area of 36 square units. Actual is key, 36 units is key. What is the scale of the drawing? Each square on the grid has a length of 1 unit. So remember, we want to do our setups scale to actual. So remember, our fractions need to be set up scale to actual. Okay, so I'm going to find the area of this thing, the little one, and then I'm going to compare it to the 36 and figure out what's going on there. So 1, 2, 3, 4, 5, 6. So this is 6. And then 1, 2, 3. So this side is 3. Okay, so now the area of a triangle is 1/2 its base times height, which means I'm going to do 1/2 6 times 3. Half of 6 is 3. And then I need to multiply by the other 3 that's there. So the area of the drawing is 9. So the area of the drawing is 9. The area of the actual is 36. That came from my problem. So the area of the drawing, or the scale, is 9. And the area of the actual is 36, came from my problem. If I were to reduce this, we get 3/6, which reduces again to 1/2. Oh, no it doesn't. Silly Miss G. 3/12. That's what I was looking for. 3/12 and then 1/4. Silly me. Okay, so what that means is that I multiplied something by itself to get 1/4. So my question now is, what is that number that I had to use to get 1/4? Well, here's how I want you to think. I want you to think, what times what gets you 1? It has to be the same number, and that's got to be 1. And what times what gets you 4? The same number, and that would be 2. So that means that your scale factor is 1/2. So that answers the question, what is the scale of the drawing? The scale is 1/2. The common mistake is that kids will stop here and call it 1/4. But it's not. You need to back up and say, what times what gave me that 1/4? Because that represents your scale factor. These are areas that you were working with. They weren't straight dimensions. So since you're working with areas, you have to back it up another step and say, what times what gives me this ratio? That's where kids get confused a lot. So this 1/2, that actually answers the question. What is the scale of the drawing? 1/4 is your ratio of your areas, which eventually leads you to your scale. Okay, so now we are going to skip this one. You don't need to do this problem. You are going to go to the problem set, and you are going to do number 1, which is just like the problem we did. So go back to that exercise if you are confused on how to do that. You don't need to do number 2. And I do want you to do number 3. Okay, so you're going to do numbers 1 and number 3. That's it. That's all I'm asking you to do. Be good for the sub, and I will check your problem set tomorrow. Bye, guys.